identified correctly the formula or the identity, I should say, that needs to be used here, right? So this is definitely 1 minus cosine twice x over 2, and this is definitely 1 plus cosine twice x over 2. And because I keep forgetting, allow me to stop here for a moment and list all the identities and everything that you need to remember from chapter 7 or for chapter for the next test, okay? Because then I will forget. Or I continue and you will remind me after I finish to list them.
I'll remind you, please.
Thank you. Okay, so this is 1/4 indeed. You correctly identify that this is a minus b times a plus b. So this is 1 minus cosine squared twice x, which was fine, right? This was in our contract 3 months and a half ago. A minus b times a plus b, correct? Okay, now I'm facing another problem here. So initially I had sine squared and cosine squared, and we said no powers, just power 1 on everything, and everything has to be in cosine. Whatever argument, I don't care, but power 1.
Right.
Yeah. So now I have to apply the same formula again for cosine squared twice x.
Right.
So I have 1/4, 1 minus, and I write it again. Can anyone say what I should write? One.
Plus cosine 2x.
But if this is 2x, I cannot write 2x. Exactly. Cosine 4x divided by 2. Basically, I'm done. There is only cosine in the formula, and that cosine has power 1.
Right.
But I would like you to work on it a little bit and simplify it, because it's okay. It's what we should do. Leave the 1/4 alone for a moment. Keep the 1. You have to distribute, break this up into 2 fractions. You have to distribute -1, so I have -1/2 and -1/2 cosine 4x. So always look at lists as separating. This is one way. It's okay if you write, I don't want to separate it. I would rather find the least common denominator. Fine. So you find the least common denominator, and then you write 2 minus 1 minus cosine 4x. That's another way. So let me write it here.
Why wouldn't it be plus half cosine 4x?
Because you have minus in front, and minus has to be distributed to both terms.
Oh, okay.
You cannot just distribute it to 1. So if you separate it into 2 fractions, 1/2 plus 1 over plus cosine 4x over 2, you still have to distribute
You're still
the sign.
distributing negative.
Right. Or I'm going to write here or. You can write 1/4. Change this into 2 over 2. Multiply it by 2, right? It's 1 over 1. So 2 minus 1 minus cosine 4x over 2. If this is better, write this. You still have to distribute a negative sign to both at the top. So negative in front of a fraction line gets distributed to everything at the top.
Right.
If it has 2 terms, to all both. If it has 5 terms, to all 5 terms. Okay. So here you'll have 1/4, and 1 minus 1/2 is 1/2 minus 1/2 cosine 4x. And all you have to do is distribute 1/4, and you're done. So 1 over 8 minus 1 over 8 cosine 4x. I hope you agree that this is way more human than the problem we looked at in class some time ago.
Yes. Yeah. That.
So this was basically 3 rows. The other one, it took me 2 pages.
Yeah.
So here you will get the same thing. You will still have 1 minus cosine 4x. 1 over 2 times 1 over 4 will be 1 over 8. And then minus cosine 4x over 2 times 1 over 4 will be this.
Yeah.
So the answer reduces to, of course, the same thing. Any questions? Okay, very good. So now let's look at the list. I don't want to forget. So the list of identities that I would like you. Any questions here, Nico? Is this okay? Anybody? Arim? Okay, Arim. So number 2. Page 2, I meant to say. So formulas, identities, whatever you want to call them. Here's the list. Sine, cosine. So I need to remember this, right? By now, I'm sure you're dreaming about this. Okay, then on the unit circle, I need to remember, although I shouldn't have to, 1 comma 0, 0 comma 1, negative 1 comma 0, and 0 negative 1. I shouldn't even write this down because we know those coordinates, right? Right? And we know that cosine is measured where?
Yeah, exactly.
Correct. So then cosine will always be the x coordinate. So 1, 0, negative 1, 0. And sine will be 0, 1, 0, negative 1. So sine is measured on the y-axis, is always the second coordinate or the y-coordinate. And cosine is measured on the x-axis, is always the x-coordinate. Perfect. We need to remember that sine squared alpha plus cosine squared alpha equals 1. And the ones that come out of this one. And there are several. One of them is sine alpha plus or minus the square root of 1 minus cosine squared alpha. The other one is cosine alpha equals plus or minus the square root of 1 minus sine squared alpha. And we know how we get these, right? We solve for sine squared and we take the square root from both sides. Right? Okay, then we have 2 more actually, not 3, I'm sorry. So we have 1 plus tangent squared. Tangent always goes with secant. If you remember this, the fact that tangent and secant go together, you will remember the derivative of tangent in the next class, which is secant squared, by the way. Which will be the rate of change of tangent at any point where it exists. And then 1 plus cotangent squared alpha equals cosecant squared alpha. If you remember that cotangent and cosecant go together, again, it will help you in the next class. Okay. Any questions? 1 plus tangent squared secant squared, 1 plus cotangent squared cosecant squared.
Yeah, but it's, I'm going to write it in terms of 1. I think that's better.
Say it again.
Well, I said I'm going to write it in terms of equal to 1. I'm saying I think that's better.
But then you have secant squared minus tangent squared equals 1. Nobody remembers it like that, but if that helps you, it's fine. That's fine. But not plus. Just make sure.
Yeah, minus.
Secant squared minus tangent squared equals 1. That's fine. Cosecant squared minus cotangent squared equals 1. That's fine. Okay. Now, the rest of the identities are the tangent, what tangent equals to, sine over cosine. I shouldn't write that, right? Cotangent is 1 over tangent, or cosine over sine. Secant is 1 over cosine, and cosecant is 1 over sine.
Yeah.
Okay. Then the cofunction identities. Sine pi over 2 minus alpha, then we have tons of them, right? Equals cosine alpha. Cosine pi over 2 minus alpha equals sine alpha. Tangent pi over 2 minus alpha equals cotangent alpha, right? So let me write 2 more. So tangent pi over 2 minus alpha equals cotangent alpha. These are cofunction identities. Let's also write secant pi over 2 minus alpha equals cosecant alpha. Then sine alpha plus beta or minus beta. Cosine alpha plus or minus beta. and tangent alpha plus or minus beta. You want me to write those definitions, those identities? So this is sine alpha cosine beta plus or minus sine beta cosine alpha. And this one is cosine alpha, cosine beta minus and plus sine alpha sine beta. And this is tangent alpha plus or minus tangent beta over 1 minus plus tangent alpha tangent beta.
Yeah, with sine plus and cosine plus and minus.
Yes.
Plus.
Yeah. The cosine is the only one that is twisted. Then the double angle and the half angle. You're not responsible for product to sum and sum to product. Those will be given to you. And you're not responsible for tangent alpha over 2 other than the ratio. The other two forms will be given to you. So sine twice alpha to sine alpha, cosine alpha. Cosine twice alpha equals cosine squared alpha minus sine squared alpha and 1 minus 2 sine squared alpha or 2 cosine squared alpha minus 1. This is the only one with 3 options. And tangent twice alpha is 2 tangent alpha over 1 minus tangent squared alpha. You don't have to copy them down now. Just copy them here where you have them.
Yeah, I mean, I was at the last part.
Oh, yeah. So sine twice alpha, cosine twice alpha, and tangent twice alpha. And then the last one, sine squared alpha, 1 minus cosine twice alpha over 2. That's the lowering powers. Cosine squared, 1 plus cosine twice alpha over 2. And these are the same formulas for half angle. So sine alpha over 2 is the same thing. I'm going to copy plus or minus the square root of 1 minus cosine alpha over 2. And the last one, no, I didn't mean tangent. Cosine alpha over 2 equals plus or minus the square root of 1 plus cosine alpha over 2. Anything else will be given to you. Actually, I have enough to test you on. I don't need extras. Anything else before we go back to chapter 4? Yeah. Okay. So we are ready now to start 4.3, which deals with logarithmic function, or logarithmic functions, I should say. 4.3. Very powerful function. A lot of real-life applications, as I mentioned last time, like the exponential, very powerful. And you could say, don't we have enough? Couldn't they just use polynomial functions or rational functions? No, because there is no polynomial function that does this, and no rational function that does this. So it's totally special. And there is no rational function that will be graphed like we're going to graph the log. Before we look at the graphs, although we have them, we graphed them already. Let me remind you what we graphed last time as the inverse function. We graphed something like this. That was one option. And the second option was something like this. No polynomial function does this, no rational function does this. This is totally different and separate and very powerful, actually, as I said. Okay. The most important concept in this chapter, I'm going to write very, very important. First, I'm going to write it in plain English, and then we'll change it into math. So here it is. Any exponential equation can be changed replaced by whatever you want. What do you prefer? Changed into or replaced by? I'm going to put in parentheses. You use whatever you want. Any exponential equation can be changed into or replaced by, exactly, a log equation. Comma, and vice versa. This is the most important concept in this chapter. Why? For several reasons. One is it shows you the mechanism that is the inverse mechanism from an exponential. I apply an exponential to 5, and I get a number. Well, I apply that log to this number, and I get 5 back, right? So it shows the mechanism between the two functions. Secondly, without this concept, I will have difficulties in solving either exponential equations or log equations, depending on the equation. But knowing that I have the alternative, you give me a log equation, I'll say, I don't know how to solve it, but I can change it to an exponential, and I can solve it. You give me a sophisticated exponential equation, I say, I'm going to change it into a log because it's easier. So at least 2 reasons, very powerful reasons, very important reasons. So here it is. How we write this in math, because this is just English, right? Okay. So bear with me and tell me whether a to the x equals y, whether this is an exponential equation. A is the base, y is the output, whatever you wanted it to be. So in other words, an example of this will be 2 to the x equals 4. So x is the variable. Is this an exponential equation?
Yeah, yes.
Okay. This will be always equivalent to, and this is the double equivalency. What does this mean? It means that, you will see this also in calculus. It means that this equation can be changed into this equation, and this equation can be changed into this equation. That's a double equivalency. I start from left, I can go to right. I start from the right, I can reach the left. Okay. So now the notation for log is log, L-O-G. Log in base A, it must be the same base. Apply to y equals x. And now the obvious question is, from you to me, how did you get this? How did you get from that to that? So what is log? Log applied to this, right?
Mm-hmm.
So log is a power. I'm going to show you the mechanism in a minute, how we go from one function to the other. Log is a power. The power we raise x to, so see, the answer of log is the number, but is actually a power. So when I say what is log, I'm going to say power. A power, the power I raise its base to get a particular number. So before we do this, just tell me how will you change this? Just give it a shot. I know this is the first example and it's difficult.
Log plus 2 divided 4 equals 10.
Yes. So how do I go back? Base raised to x equals 4.
Yeah.
Base raised to x equals 4. So log is the power that I raise its base to get a number that I apply log to. So let's look at a function. Give me an exponential function f of x equals any exponential function you can think of. We looked at few. We looked at one with base 2. We looked at one with base 3. We looked at one with base e. We looked at one with base 10.
Yeah.
10 raised to the x, fine. So let's say x equals 1. What will be the y value?
10.
Yes, perfect. So now I want to create a mechanism in such a way that this will be the inverse function. We're going to write it in a minute. So that when I apply f inverse to 10, the result is definitely 1. Okay. So it will be a log. Which base?
10.
It has to be the same base of x. So this will be the inverse function. However, what was base 10 raised to x named? 10 raised to x was a function called the common. Remember, there are two functions that we gave special names because they are in the calculator and they're so useful. One is called common if it has base 10, and the other one is called natural if it has base. Perfect. So we will not be using this notation. Nothing wrong with it. You are not going to be, I'm not going to take points off if you write log base 10. But we write it like in the calculator, log. And it is assumed that it's base 10. It's like the square root. You can say I don't see the index. This is the only one for which we do not write the index. And the index is 2. So because the graphing calculator, if you look at the graphing calculator for a moment, you will see log. You will not see log base 10.
Okay, so just so I understand, so are we saying that 10 to the x equals log to the x? Is that what we're saying?
We say 10 to a number equals 10. I didn't finish. I didn't show the mechanism yet, but you're ahead of me, which is awesome. But I did not get to that. So now I want to show that f inverse of 10 is 1. I have not shown that yet. So in other words, I want log of 10 equals a number. I don't know what the number is. I don't seem to be able to solve a log equation. I don't know how to solve it, but I know how to change it into an exponential equation. What is the base here?
10.
Okay, so 10 raised to whatever is 10. So I'm going to write that because I don't know how to solve this. But I'll say, let me change it into an exponential equation. And now you will clearly tell me what the number should be.
What?
Yes. So indeed, f inverse of 10 is 1. Okay, let's choose another number. Let's say x equals negative 3. For this function, 10 to the x, I have 10 to negative 3, which is 1 over 1,000. Do you agree? Correct?
Yeah.
So now the question is, how much is log of 1 over 1,000? And I'll say to you, I have no clue. I don't know how to solve this log equation. It's too difficult for me. But I know that I can convert it into an exponential one. So how do I convert this logarithmic equation with whatever number? You can put y, a, b, c, whatever you want here, doesn't matter. So I will say the base
10.
raised to this number equals this number. So 10 raised to a number equals 1 over 1,000. So what is log of 1 over 1,000 equal to? So when I apply the inverse function to this number, what do I get back? There is no chance, but other than -3, I can't get anything else. So that's how the mechanism works. Any log equation can be changed into an exponential, and any exponential can be changed into a log. You can always go back and forth. I would like to practice going back and forth right now for a few minutes, and then graph of a couple of log functions. I'm on page 322. Feel free to choose from 322. I would like to choose problems step by step, 1 or 2 from each set of problems. Let's say between 7 and 40, page 322. So from each set, choose one. If we need more, we'll choose more. Let's say from 7 to 12, express the equation in exponential form.
12.
Which one?
12.
Very good. So let's look at 12. A or B or both? Okay, so 12a, we have natural log x plus 1 equals 2. Okay, so before we continue, allow me to, yes, I'll explain in 1 minute. Yes, indeed. So natural, common, the exponential function, the natural function, ln. It should be NL, but it's in German, so it's log natural, not natural log. So we kept that, ln. So common, f of x equals 10 to the x. And what is the common log function? Yes, with no base. Correct. But we know that the base is 10. So then, our equation ln applied to x plus 1 equals 2. Remember natural log or log, common log or any log, does it belong to the friendly category of functions or the not friendly? Or not so friendly? Not so friendly. It's not defined everywhere, and it has a vertical asymptote. It's in the same boat with radicals, rational functions, tangent, secant, cosecant, cotangent. Yes, the same category. So function with ringing a bell in our head. Oh, I have to be careful. Good. So they are asking us to change this into an exponential equation. I always start with the base. E raised to, yes, equals x plus 1. They're not asking us to solve it. But how will I solve this equation for x? That's it. So it's e squared, which is a number, minus 1. And it's done. Okay. Now, knowing this, so let's refresh our memory on the exponential and log. What is the domain of the exponential? So when we talk about the domain of the exponential, always we should ask ourselves, is it friendly or not? It's very friendly. It's a very good function and friendly. What is its range? Keep in mind the graph. The pure exponential function, not the ones with transformations, I have no idea. But the pure exponential function
0 to infinity.
is 0 to infinity. So what will be the domain of the log?
0 to infinity.
Correct.
Range of negative infinity to infinity.
Perfect. Now, if you give me any log, like for example, if you give me any rational function, I'll say, oh, the denominator cannot be 0. If you give me a radical function, I'll say if the index is even, the quantity underneath has to be greater than or equal to 0. If you give me a log function, like you just picked this one, if you ask me what is its domain, I'm going to have to write this greater than 0. Which means, and I know that, because this is a shift where, which direction? Which direction is this shift?
To the left.
Yes. So that's why the domain is from -1 to infinity. So x greater than -1. So the domain of this function is -1 to infinity. The pure log function starts at 0. Here it is. Here's the pure log function. 0 to infinity. Its domain for any pure log function with no transformations in it, the domain is 0 to infinity. But this one is a horizontal shift of 1 to the left. That's why the domain is -1 to infinity. Okay, the next set, 13 through 18. Will you change, because I don't want to avoid, bless you. Can anyone tell us B? Because you mentioned that, I don't want to skip. What will you write for B? So for B, we have natural log of x minus 1.
E to the fourth power equals x minus 1.
E to the fourth power equals x minus 1. That's it. Let's choose from 13 through 18. Although these are easy problems, I would like to build up our knowledge slowly.
16.
Okay, 16. So in 16, on page 322, we have 4 raised to -3/2 equals 0.125. So please watch this for a second. In this problem, we are asked to change it into a log. So I will write log. I have to have something here as the base. I have to have something here as the number I apply log to, equal symbol, and something here. And obviously, this raised to this has to be this. And the base for exponential and the base for log, otherwise they will not be inverses of each other. Because imagine the base 2 applied to 2, 2 squared is 4. Can I apply base 3 here to get back to? No, it has to be the same base. Both directions, right? So the function has to have, exponential function has to have base 2, and the one that comes back as the inverse has to have base 2. Otherwise, I can't solve. So, of course, the base is 4. 4 raised to,
-3.5.
of course, it must be,
0.125.
yes. Some calculators, I don't know if mine here, the software does it, allow you to put in the base you want. I will show you the change of base. If you don't have it in math, I don't know, I've never checked. I don't know if this software has it.
Go to math, and then all the way down.
Okay, so it does have it. However, I will still ask you to remember the change of base formula because at some point in time you may need it. So let's assume that we don't have log base in there in which we can put whatever base we want. In that case, I would like to, from any base, to change into one of the two that we have in the calculator. All calculators should have natural log and common log. So let's suppose I would like to determine log base 3 of 4. And you can say, that's a piece of cake. No problem. So it's a number. And you could say, we know you're not capable of solving this equation, but you are capable of solving this equation. What equation is this equivalent to? Raised to
X.
whatever
Yeah.
equals,
Four.
I can't solve this. I won't be able to. I cannot give you a number that I raised 3 to get 4. I can't. I'm not capable of doing that. So I can still determine this with big accuracy, good accuracy, but I have to put in the calculator. So assuming I don't have an option of putting base 3, I only can change this, let's say, into either common log, which is base 10, or natural log, which is base e. So here's the formula. Log of 4 over log of 3. What should I write? A wild guess. If I don't want to use log, but I want to use natural log.
4. Again, natural log 3.
Should I get different numbers? Should I get here 1.3 and here 1.2? What do you think? There is only one number. I raised 3 to get 4, not 2 numbers. If this is 1.4, it's 1.4. Nobody can find another.
Yeah.
Functions are 1 to 1, right? For each y, I get only one x. For each x, I get only one y. So these have to be the same. So if you put them in the calculator and determine log 4, close the parenthesis, divided by log 3, or you get natural log of 4 divided by natural log 3, I have to get the same answer. How will I check my answer? I want to check my answer. I don't trust this.
You can
Raise
4
raise 3 to this previous answer. So 3 caret previous answer. And when I click enter, what should I get? So the answer of this is 1.2619, depending on where you want to stop. 1.2619 approximately. Okay, next set, evaluate the expression. And the next set is asking us to solve an equation. I will not emphasize the formula 25 and 26 because it's required in Calc 2, but I'm more than willing to show you. So if you want to choose anything else. Which one?
28.
28. Very good. So we're looking at 28 log base 4 of the square root of 2. I have no idea what it equals to. But I know that this now, after I put the question mark in there, I know that it can be changed into an exponential equation. So let's change it into an exponential equation. Okay, my department decided that I'm on the calculus committee, not on the pre-calculus committee, so they decided 5 to 29 odd, so I need to show you that. However, I will not put it on a test. It's not a difficult formula to understand, but I just think that not useful right now. But I will show you. Okay, so this is a log equation. By putting a question mark in there, I transform it into a log equation. And I know that it can be changed into an exponential equation. How do I change it into an exponential equation?
4 raised to a number equals square root of 2.
Yes, 4 raised to a number equals the square root of 2. I only learned very basic exponential equations. Right now, I don't know more. So what am I trying to do and have on both sides? The same
Base.
base. Okay. So can anyone give us a base for 4? There is only one, which is squared to some number equals,
2.
yes, awesome. So the left-hand side will be, maybe it's easier if I write this an A here, so it's not, doesn't look like a square question mark. Or it's not, confusing. So then the left-hand side is 2 raised to which power?
2. No, I'm sorry. A plus 2.
Which operation I have to perform with 2 and A?
2A.
Very good. Equals 2 to 1/2. So therefore, we have two numbers that are equal, and they have the same base. What has to happen to the exponents? Again, I'm not canceling, I'm not simplifying, I'm not removing the base. I'm thinking. So then 2A must equal 1/2, therefore A must equal 1/4. So what is this answer here then? Log base 4 of the square root of 2? 1/4. Very good. So maybe we should choose another, and also from 25, 26. I think we should choose another.